Hello, my name is Georgia Herr, and I'm a junior studying environmental engineering. This semester, I worked with PhD student Sarah Orbel and project director Dr. Terry in the College of Civil, Constructional, and Environmental Engineering on my project titled Characterizing Contaminants Throughout Wastewater Treatment Processes and Assessing PFAS Contamination in Alabama Water Systems. First, I'll go over some of the main objectives of this project and some background information, and then I'll get more into the specific work that was completed this semester, and finally I'll go over some of the future goals of this research. So this project has two overarching main goals. The first goal is to study a variety of contaminants entering a wastewater treatment plant, which are listed here. This wastewater treatment plant is a real plant that is currently in operation and utilizes a system called indirect potable reuse, which is where the effluent leaving the wastewater treatment plant passes through an environmental buffer and then is used as influent into a drinking water treatment plant. And since this water is ultimately reused as drinking water, it's very important to monitor the contaminants that are exiting the wastewater treatment plant. The second main goal is to determine the extent of PFAS contaminants in water utilities both in the US and specifically in Alabama. As you can see in the first goal, PFAS are a contaminant of concern in wastewater, so it is important to map the extent of contamination in these water utilities. These boxed items show what I was able to contribute to specifically this semester, which was characterizing TOC, DOC, and TSS contamination, as well as some data analysis of PFAS contamination in the state of Alabama. I'll go over each of these experiences one at a time, and I'll start with some background information on what each of these contaminants are. First, I'll go over TOC, DOC, and TSS. TOC stands for total organic carbon, and this is a measurement of all of the organic carbon that is contained in a wastewater sample. DOC is a subset of this carbon, and it is dissolved in the water, which means that it is more difficult to remove with filtration processes. Total suspended solids are a measurement of total solids in a wastewater treatment, in a wastewater sample, in this case above 45 micrometers. And all three of these are very common metrics for measuring wastewater quality, and in general, at the end of a wastewater treatment process, we want to see all of these contaminants at very low levels. This is a diagram of the wastewater treatment plant where those samples were collected to test for TOC, DOC, and TSS. As you can see, the wastewater enters the plant on the left of the screen and flows to the right through a variety of treatment processes, which are each assigned a number 1 through 17. For this analysis, grab samples were taken from sites 1 through 14, which is the main flow of the water through the plant, and then analyzed in the lab for contaminants. This graph shows the results of the TOC and DOC levels throughout the plant from September of this year. As you can see, the TOC and the DOC decreased drastically in those early sites, and then by site 14, there are very low levels of TOC and DOC in the samples, which is good. Similarly, the TSS results from that same time show that there are very low levels of TSS by the time the water reaches those later sites, which also shows that the TSS removal is effective in these treatment processes. So both of these results are good because they show that this plant is functioning properly in removing these three major contaminant metrics. So just to summarize the results that can be concluded from this data, there is an effective decrease in all three metrics, especially in the beginning treatment processes, which is an ideal result. And then for TSS specifically, that is most effectively removed in the secondary clarifier, which is site 5 in this diagram, which is also a result we would want to see. So although it is important for this wastewater treatment plant to be monitoring TOC, DOC, and TSS, this plant's main concern in regards to this research is its levels of PFAS contamination. And although we weren't able to accomplish any measurements of PFAS at the plant this semester, I was able to contribute to that second main goal I mentioned of examining PFAS contamination data in the state of Alabama. For some background on PFAS, PFAS stands for perfluoroalkyl and polyfluoroalkyl substances, and this is a group of thousands of synthetic chemicals that contain a carbon-fluorine bond. This bond is very, very strong, which means that PFAS are very hard to break apart and they don't break down naturally in the environment, which means that they are often referred to as forever chemicals. Removing these chemicals from water is a major issue in water treatment today. As you can see in this graphic, PFAS are found in a wide variety of things that we interact with every day, like food and consumer products, and most important to our research, our drinking water. We know that PFAS do have adverse health effects in humans, so it's very important to limit the amount of PFAS that we are interacting with in our drinking water. Recently, new drinking water regulations for PFAS were released in the United States, and these are going to become enforceable in 5 years in 2029. This graphic summarizes these regulations. It shows a variety of common PFAS and their maximum contaminant levels that will be allowed in drinking water. So it's very important for water systems across the country to be monitoring their systems for PFAS contamination during this time in order to be prepared to be compliant with these regulations in the next 5 years. What I was able to do this semester was to assemble publicly available data from 2019 to 2023 of PFAS contamination measurements that have been taken in the state. This data is available through the Alabama Department of Environmental Management, but it's in a very inaccessible format for data analysis. So what I did was I organized this data into an Excel file that is sortable both by measurement and by PFAS type, which makes it much easier to use for analysis. One example of analysis that can be done with this information is this map here, which shows the average PFAS concentration of measurements by county in the state of Alabama. As you can remember from the regulation slide that I showed you, an average measurement of around 10 would be ideal because for many PFAS, that maximum enforceable level is 10 parts per trillion. And so that would be these lighter blue counties in this map. So you can see that there's several counties that are darker blue, which shows that these counties have had several measurements that would be above these regulatory levels. However, you can also see there's a lot of gray counties in this map, which is counties that have little to no data. So this just goes to show that this data set is definitely not comprehensive and is not perfect for drawing any sweeping conclusions about PFAS contamination in the state. So a key goal of this research moving forward is to start taking those measurements for PFAS contamination at that study wastewater treatment plant that I mentioned. This can be done by measuring adsorbable organic fluorine in wastewater treatment samples, which is a helpful estimator for estimating the total number of PFAS in a sample. And the reason that this work wasn't started this semester was because the lab didn't have the necessary equipment to complete these measurements, but the lab has recently acquired this equipment, so hopefully this work will start next semester. So to summarize the main goals of this research moving forward, the major goal will be to finish 1 year of sampling and analysis for AOF and PFAS at the sample wastewater treatment plant, and then to develop a method for measuring AOF in biosolid samples as well as the wastewater samples coming out of the treatment plant, then to analyze these results for any potential interferences or biases, and finally to examine this data in the context of the flows that the plant is receiving and as future plans in terms of regulation. All of this work, as well as what was completed this semester, is going to help advance measurement of PFAS using AOF, as well as help this specific wastewater treatment plant determine what its next steps will be in managing its water treatment processes. Thank you. Please let me know your questions.
You mentioned that PFAS are very difficult to remove from the water supply and water treatment plants. Could you go into some detail on some ways that it can be removed if it's possible?
So going back to the PFAS slide, they are very hard to break down, which is a way that many contaminants are removed from water, so that is a challenge. So typically it's more of a storage and making sure that they aren't entering the water in the first place is the primary first step.
In the graph on slide 7, why is there no data displayed for site 4?
Okay, going back to 7, yeah, so you can see here that it skips straight from site 3 to site 5, and if I go back to this diagram of the wastewater treatment plant, you can see that site 4 is the biological reactor basin, and what happens here in a wastewater treatment plant is that microbes help to break down those organic contaminants, so there are a lot of microbes in this basin, and it makes the sample taken from that basin very, very sludgy and thick, and it's so thick that it's unable to be analyzed for TOC and DOC.
Could you tell me what the PFAS monitoring data looks like for the whole country versus what you've looked at in Alabama?
Yeah, so the EPA has public water systems monitor for PFAS starting in 2023 because they have a list of unregulated contaminants that they want to see monitored in public water systems. So that data has been coming out for over a year now, and it does show pretty concerningly that PFAS are a problem everywhere to different degrees, so it's certainly not unique to Alabama. They're typically highest in places that have had a lot of industrial activity or are near landfill sites, but it is definitely a problem across the country.
In the graph on slide 8, why does the total suspended solid concentration increase, then decrease bit to 0, and then increase again?
Yeah, so you can see that this graph is definitely not as clear and gently sloping downward as the graph for the TOC and the DOC. And so going back to this diagram again, total suspended solids, the key things here are it's small so it doesn't filter out well, and it's suspended so it doesn't settle well. And you can see in those first 3 treatment processes, that's just a screening removal and then a settling clarifier, so neither of those really affect the TSS levels, and then it goes through that biological reactor basin that I was mentioning, and by the time it hits the secondary clarifier, which is that site 5, it's able to settle out much more effectively, so we see that big drop. But then there is that resurgence again at 8 and 9, and going back to this diagram, you can see there's actually a split of the flow of the water at 5, so even though 8 and 9 is a greater number than 7, 7's actually a little bit further along that treatment process than those 2 points. So although these numbers are generally in order for the water flow, they aren't exactly in order.